Yeah, I had some problem with this. Okay, so what was wrong? Well, so yeah, well, I had problem with this function counter. So let's try to correct it a little bit. So not sure what was problem. What so should I rerun everything? Yeah, well, I guess I should rerun everything. Okay, I will try to finish this assignment today. So yeah, yeah, today's plan is actually spend 4 Pomodoros on this course. Then I will like do some break. After that, I will continue statistic course on Khan Academy. And after that, I will do like 2 additional Pomodoros of ML course. So I think it should be enough for this assignment at least. Okay, well, I got main ideas, but yeah, implementation is not so easy sometimes, but I guess it will be more clear further. So yeah, here I tried to build a tree, a decision tree connected with task. Yeah, not sure. Yeah, I succeed with it, but oh well, this picture is much better. Yeah, well, I succeeded with it, but yeah, I found some solution. Not the best one, cause I can't manage to can correct it somehow in my ways. I don't know, can't like increase the size of the picture or something like that. Okay, so yeah, here. Okay, so yeah. Here we have like some example. Yeah, the goal is to like build some write some functions. Yeah, well, where I so so yeah, well, I need to find library for this function because I took it somewhere. Counter function Python. Maybe I should. Yeah, okay. Maybe I. Yeah. Maybe I can just like find some Okay, so let's try to use this one, maybe. So I guess, yeah, that's better one. Yeah, so okay, let's try to analyze it a little bit how this function works. So here we got list or vector, I don't know. There we define length of this vector. Then yeah, if we have length less than 1, so it's 0, then we don't have any entropy. So, or if even if we have only one element, it's even better. So we just return 0, cause entropy of one element or 0 elements is 0. Yeah, and after that, what we are doing? We are doing bin count labels. Not sure what it is. Let's check it out. Bin counts. I guess it gives us like unique elements, something like that. I don't know. An array of integers if counts occurs of which each bin value is occurrence. One goes that the bin size. Okay, so what again? Have number of occurrence of which value in array of negative or non-negative means. Yeah, well, so yeah, like I said, it's count. Yeah. Okay, so this must be list. Okay. Okay, maybe I should even print count. Okay, after that we calculate probabilities of each of them. So okay, print and okay, so not sure why we are calculating. Yeah, well, I guess we want to change base of logarithm, but if, for example, we have 3 or more logarithm, like okay, so print and classes. Okay, so and okay, and here let's call it one more time. Okay, so yeah, we have two classes, like 11, like 11 elements in the first class and 9 elements in the second class. And yeah, and after that, okay, so I need to see again read article. What was the, yeah, well, I thought that the base of this logarithm must be true, and so if the number of classes will be like in the last example will be 6, so the basic of logarithm must be 6. 1 1 1 1 1. Well, I'm not sure that paradise. Okay, so okay, well, yeah, well, I think I can stop with it. Just yeah, well, so well, I have the function for entropy. Okay, that's good. Okay, now we have information gain. So okay, we have, what is root? Root minus initial data left and right, two pairs of initial data. Ah, root is initial data. Yeah, okay, I got it. Okay, so okay. Well, yeah, I know how to. So yeah, I need to build like this function. Yeah, but I'm not sure how to define left and right in the code. So okay, so let's try to write it like I think it should be. So yeah. Not sure that it's true. So entropy init would be something like my entropy function, not exactly mine, but who cares, of root. So yeah, and we have two groups. Yeah, so let it be entropy left and entropy right. And okay, and okay, so here we'll have left, and in the last one we'll have right. Okay, so we have 3 entropy, and what we need to do is to return information gain. So it will be initial entropy minus length of left divided by left length of root, and this one I must multiply by entropy left, and same for another, but here we need to write. Okay, yeah, well, we have this, so okay, and yeah, well, I think, yeah, there is some gaps. So what if length of root will be 0, and so on, but yeah, I don't need like to pass every test. I need to like build function for my case. So let's try to not go very deep here. Information gain, false. Oh, another one. False left, false right. Left, false right. So yeah, I expect it just to from this just work. Yeah. So okay, one more time. Okay, so here I need to remove additional comments, because every time I run my function entropy, it will give me like another information that I don't really need. Yeah, so this is my information gain. Okay, and best feature to split outputs information gain when splitting on best feature. Well, I'm not entirely sure how to do it. Well, because it obviously must give me like the like maximum information gain. So how can I do it? So okay, well, I think I can check it on. They did something very close to this task on the video lecture, so I can check it by myself. How is it? What they did? Yes. So Okay, so they built like tree, they train it. So they're doing cross validation here. Yeah, not so sure what I need to do here. Yeah, well, maybe I will skip it, and I want to. So yeah, I will go. Yeah, after the break, I will go to the last part. So yeah, and I will check what they want from me here. After that. Okay, so be right back. Okay, let's continue. So okay, part 3, dataset description, adult, no need to download it. Okay, classify people using demographical data, whether they earn more than 50,000 per year or not. Okay, feature description: age, work class, FNLVG, final weight on of object, continuous feature. Okay. Education, categorical feature, educational none, number of year of education, marital status, categorical feature, education, relationship, race, sex, capital gain, hours per week, country, target, earning level, categorical binary feature. Okay, so try to look at this data. Okay, so we downloaded it. I guess tail gives us last 5 individuals. So age, work class, what it is, educational, okay, educational, occupation, relationship, target. Same, we download data test. So there we will like get our answers. Third rows with incorrect labels into. So okay, so did we get rid of it, or we just renamed this like string to the 1 or 0? So let's check. Yeah, we just okay. So yeah, we just renamed. Okay. Okay, so we renamed. So age. What is wrong? So okay. So we have these numbers of people who earn less than 50k and these more than 50k. and here we plot something. So here we plot so here we iterate for every column in the data. Here we just plot this thing. We just plot every diagram for every data, I think. Okay. So what have we done? So if type of data is equal to object, so data column value counts plot bar. Else the string. So for example, age. For every non-object we build bars. For another one we build histograms. So okay. So yeah, for continuous data, for int data, for every numerical data we use histogram here. For another one we build for categorical one we build bars, something. Okay. And okay. The same data, I guess. It's actually has some problem with so yeah, well, we see that in different data sets we have different types for the same column, so we wanted to have all the same, so we will get everywhere into something. So in train in test, yeah, we want to have everything like in train data. So here we renamed it. Okay, so fill in missing data for continuous feature with the median values. For category which features with the mode. Okay, so here we are dealing with missing data. See some missing values. Info. So and here we are filling. So see in categorical columns. So here okay, so if our object has name object, if our data has name object, has type object, we named as categorical data, and in another case we are naming numerical data. Yeah, so and we are filling missing data as as it mentioned below above. Okay. So well, I see. So we have in total 32,000 and 561 entries, and as we can see, so for example in work class we don't have like every we don't have some entries, some of them missing. Yeah, I see it right now. So yeah, yeah, now every entry has maximum value of it. Okay, so we just before we just prepared some data. Okay, we will dummy code some categorical features. It can be done via pandas method get dummies. Okay, so we built our data, and now we drop target vector from each of matrices, and yeah, we have like full data for our training. Okay, train a decision tree with a maximum depth of 3 and evaluate the accuracy metric on the reduce pen to render state for results representative. Okay, so how have I done it? So I've already built some tree, so I need to so So we built a tree. I need to check how to evaluate accuracy. So okay, so and here we can calculate prediction accuracy. So here we built tree, we fitted it, and then something like that, I guess. Ah, yeah, well, so here the same. So instead of x hold out, we should use x test. Uh, and calculate accuracy. So y test. Okay. Okay, 0.84. Do I have this one? Yeah, 84.5. Yeah, something like that. What is decision tree? What is the test set accuracy of decision tree with maximum tree depth of 3? Well, actually, I don't know what is. Did we have random forest? Yeah, well, if you will have it in further, I will skip this. Yeah, I think we have random forests in further, so I don't want to do it. Yeah, so I just don't know what is random forest is. So. Yeah, and okay, so Well, probably in questions I will have another one. So what will happen if I will like do the same but with def is equal to 9. So same thing, but accuracy, but 3 def will be 9. So yeah, let's just 3 1 3 1 1 1. So yeah, I will just use another variables for this. Well, it's a little bit higher, I guess. 0, yeah, this one. Okay. So yeah, and last thing that I think not mentioned here, but okay, so train decision tree classifier random state is going to find the optimal maximum depth using 5-fold cross validation. Okay, so yeah, they did it on lecture, something close, so I will try to repeat it. Yeah. Okay, so yeah, well, I will do break again. And I'll restart again. Yeah, but yeah, after that, yeah, I will try to finish this one, and I'll skip this random forest, because I'm not entirely sure what it is, and they didn't have. Yes, they didn't have like really good theory in mm, they didn't give us good theory in this topic, so I guess yeah, I don't want to go much further. Okay. Oh yeah, next topic will be much harder, I guess. Yeah, it has like 5 articles, lots of videos, MN4. Well, yeah, yeah, it's just typo, so yeah, it will be 5. Okay. Okay, so let's try to finish the last part. So let's go into this lecture where they okay, so three parameters. Where is my tree? So three, two, one. Let's see. Okay. Params. Three, five. So should I use just? But I already okay. So okay. There must be some answer on. Yeah, so we got best parameters for this tree. It was maximum depth of tree. It was equal to 9. So yeah, I guess well we so yeah we were close actually by using 3. But okay, so and train decision tree with maximum depth of in compute the test accuracy use parameter. Okay, so well, didn't we already done it? So I'm not sure what it is. So hit 6 train I train and prediction. Yeah, well, I think we already done. Yeah, like here. So test. Yeah, well, I think we already done this with yeah, with 9. Yeah. Well, actually, I've done it just because of because it was on in test. Okay, yeah. So well, like I said, I will not do optional things. Yeah, I will just go through them. Okay, let's try to fill the web page. So some of them I already done. Well, it was one. What is information after split? So let's try to find it one more time. Where was so yeah, well, I haven't done this split, so 0.16. Yeah, well, I can iterate it around it to the 1. And okay, so I think I've done everything. Not sure. Yeah, well, I've done some. I did some. Well, wasn't sure that I did it right. Okay, so yeah, I had this answer before. Yeah, but I wasn't sure that it's correct. Okay, so we will see. So everything else was fine. So let's try to find solutions. I want to check how the right how the right entropy function, for example. Maybe something else. So yeah, let's try to well, and I have some question before, so maybe it will be more clear today. Okay, so well, let's start by loading all. Yeah, well, it took some time to understand this solution. So yeah, well, I had problem in the beginning, so also need the latest. So imported some data, create. Okay, so this is this here we see how they repeat what we have in our on our task. Same for solution. So okay, first question: draw decision tree by hand or graphing data set. Option: you can also implement tree construction and draw it here. Okay, so yeah, this one I got it. It was pretty clear. So this one I also got it. Yeah, it took me some time, but I understand. Okay, decision 3. I'm not sure that, I think I've done something like that. I'm not sure. I think it doesn't work for me in the beginning. So let's try to run it one time here. So not sure if it will work, but yeah, well, yeah. Main problem is that somehow it doesn't see this function. But actually, it's interesting. Did I get the same picture? Yeah, well, I got the same picture, but yeah, without some without this true false lines. But yeah, well, I got well, they actually have fancy picture, but okay. Okay, yeah, and yeah, also I didn't like use this class for the okay. Okay, part 2. Yeah, well, so for calculating entropy and information gain. Okay, so here we have same thing. Okay, so let's see. First, whenever we got um, we converted into list, then we calculate length of it, then we define entropy as 0 in the beginning, set list set elements. Not so sure what it is. Yeah, I don't know, let's Google it. What is set in Python? So I do know what it is in C++, but not so sure what it is in Python. Yeah, well, it's the same. So it's like another collection of unique elements. So it's like yeah, well, it's yeah, no, why they do this? Yeah, so okay, so what is the idea? So set will remove every like ununique elements in this list. Yeah, and it will also like sort it, so it will be better to work with it. And they also like use another variable here. Okay, so yeah, if we have only one element or 0 elements in our initial list, or all of them are repeated, so entropy is 0. But for every element in set, we count it. Yeah, we count how much does it occur in the list. Yeah, and then multiply, and then implies the function. Oh well, yeah, well, that's pretty clear solution. That's actually what I really wanted to do. I tried to use some strange functions, not strange, but I wasn't familiar with this. And yeah, well, and in my solutions that I found, I saw this kind of logarithm, which is maybe it's not like, maybe this is another like that's another approach or definition of entropy. So okay. Okay. Okay, information gain. So well, it's pretty close to what I have done. Yeah, well, I didn't use this one. I think it's just like for the type of number, so we will not get like dividing by we will not divide by the integers, so we will not get just integers. Maybe we will get something like, I don't know, example, if you divide 5 by 3 and we live in integer world, we will get like 1 and not like 1 and 2 with 230. But yeah, that's okay. By I've done this correctly. Okay, well, one more time. So whenever it will like of course, yeah, maybe it has like some problems with like testing, but no one cares, I think, here at least. Okay, so next question. Yeah, well, that thing I didn't get. I think I understood it, but maybe not so. Okay, so what they wanted probably here, they wanted to like to to iterate every possible splits probably and find the best information gain. Okay, so generate it here. Yeah. Yeah. So okay, and okay, so we iterate all over columns and information gain. Yeah. So so Okay, so well, it's not so sure what it is. So yeah, let's try to copy this and try to understand what have they done here. So I got that they built like several machine gains. Yeah, well, and probably we need like a second one. Okay, so it's working here, so let's try to understand. So what is okay, so we take okay, so we have okay, so what we have, yeah, well, I think I understand it, but yeah, one more time. So like we have vector of our answers, of our targets, y, and we have like, for example, 3 columns: x1, x2, x3, and okay, so for example, 1, 0, 1, 1, last one 0. Okay, so what am I getting from this? Okay, so what we are getting from this? Okay, so so that was the data again. Ah, oh. So we took what? We took um um so yeah, well, I will not get break here, so I want to like finish this solution. So okay, where is my data again? Okay, so what we are doing, what we are getting here, we are splitting this data using like one of the features. We are watching, like in one group we are taking like with individuals that has 0 in this in feature and 1 in this feature in the second group. So yeah, and we get like in every feature we get like some information gain. Yeah, well, I got it. Okay. And how can we implement it? Implement decision tree building grid by calling information gain recursive. What's the resultant tree? So okay, so let's try to look at it. Okay, so well, yeah, well, I will skip it. And actually, it's yeah, some sort of code I don't want to watch. Well, maybe I can like so. Okay, we took all our information gains by splitting by every features here. We choose the best one, which gives us index of the best of the max of information gains, and we got this feature. Okay, so well, I think yeah, well, I think all of this just like some kind of sugar, so yeah, just yeah, so it doesn't give us like just for fancy format of the data. So yeah, all things are here, but okay, so maybe okay, well, I got the idea. Not sure that I really need everything else. Okay, so Yeah, well, in future, I'm pretty sure that I will struggle in this part, because like to prepare my data, to prepare data for the work, it feels very frustrating for me. Okay, so feeling, yeah, well, I'm continuating it. Yeah. Not sure that I really need to see everything else, but let's try to. Yeah, well, optional. Yeah, well, I think yeah, I could just repeat everything that have done on topic, but if if I was watching while I was watching on decision trees, I had some picture in my head, but with random trees, etc., etc., I'm not so sure what it is. They gave us just main idea and some implementation. Yeah, that's not what we wanted. Okay. Okay, so I think that's it with week 3. It wasn't easy, but it has some, like, I think major definitions, major I don't know, major goals, major like setups, etc. So yeah, let's try to start week 4. Linear classification and regression. Yeah, that's like very big topic, I guess. I always I always hear about regression, classification, linear regression. So yeah, and I wasn't sure what it is. So let's try to dive into it. Following 5 articles may form a small brochure, and that's the reason. Linear models are the most widely used family of predictive algorithms. These articles represent our course in a miniature. A lot of theory, a lot of practice. We discuss the theoretical basis of the ordinary least squares method and logistic regression, as well as their merits in terms of practical application. Also, crucial concepts. Yeah, it has major concepts before. I forgot this word. Concept. Okay, so also crucial concepts like regularization and learning curves are introduced. In the practical part, we apply logistic regression to the task of user identification on the internet. It's a Kaggle in class competition. Okay, Alice, we go on with this week 4, week 6. Okay, so in week 4, in week 6, we actually will get like not educational competition. We will get like some sort of like more real competition on Kaggle. So yeah, well, it will be interesting. Yeah, well, it will not. I think I will not get answers, but yeah, who cares? It's better to admit that this week's material would rather take you 2-3 weeks to digest and practice. That's fine. But for consistency with article numbering, we stick to Okay, so okay, let's let's I don't need here. Okay, so it might took me 2 weeks. Okay, so let's try to minimize this this time. Okay. Linear classification. Okay, we will start studying linear models with linear regression. First of all, you must specify a model that relates the dependent variable y to the explanatory factors of EHS. For linear models, the dependency function will take the following form: y is equal to w0 plus, if we add dimension for each observation, then the linear form can be rewritten in a slightly more compact way by pulling the absolute term into the sum. Okay. If you have a matrix of each observation where the rows are observation from dataset, we need to add a single column of the left. We define models as follows: where dependent target variable vector of model parameters. These parameters are often referred to as weight. X is the matrix of observations and their features size n rows by m plus 1. Columns include the picture model on the left is full rank by columns. Epsilon, a variable corresponding to the random unpredicted model error. We can also write this expression for each observation. Okay, so all restrictions also apply to the model, otherwise it will be another sort of regression besides linear. Expectation of random errors is 0. The random error has the same finite variance. This property is called homoscedasticity. Okay. Random errors are uncorrelated. Estimate of weights is called linear if, where for every k depends only on the samples from X, and almost certainly in a non-linear way. In the solution for finding the optimal weight with linear estimate, the model is called linear regression. Let's introduce one more definition. Estimate is called unbiased when its expectation is equal to the real but unknown value of estimated parameter. Okay, so one of the ways to calculate those weights is with the ordinary least squares methods, which minimizes the mean squared error between the actual value of dependent variable and the predicted value given by the model. the actual weight, actual value. So we need to calculate derivative with respect to the model parameters, set them to 0 and solve the resulting equation for W. Matrix differentiation may seem difficult. Try to do it in terms of sum to be sure of the answer. Small cheat sheet on matrix. Okay, so okay. Here we took some bearing in mind all the definition conditions described above. We can say that based on Gauss-Markov theorem. It is that based on theorem OCL OLS estimators model parameters are optimal among all near and unbiased. They give us the lowest variance. Okay, so actually I'm not sure that I understand beginning. Okay, so last part was kind of fine in some ways, but yeah. Okay, so what we have done, we built some estimators, we calculate, actually here we calculate weights of which will get us what. Okay, so okay, let's try to see another thing. One could ask why we choose to minimize the mean square error instead of something else. After all, one can minimize the mean absolute value of the residual. The only thing that will happen if we change the minimized value is that we will exceed the Gauss condition and our estimate will therefore cease to be the optimal over. Yeah, okay. So I think like yesterday I wanted more theory. Well, I guess I got it. For continuous, let's digress to illustrate maximum effort estimator with a single example. Many people probably remember the formula of ethyl alcohol. So I decided to do an experiment to determine whether people remember a simpler formula for methanol. We surveyed 400 people to find that only 100 and actually I don't remember the first formula either. People remember the formula. Then it's reasonable to assume that the probability that next respondent knows the formula of methyl alcohol is okay. Let's show that this intuitive assessment is not only good but also a maximum likelihood estimate. Where this estimate come from? Because definition of Bernoulli distribution, a random variable has a Bernoulli if it takes only two values, 1 and 0, with probability theta and 1 minus theta respectively, has the following probability distribution formula. Okay. This distribution is exactly what we need, and the distribution parameter theta is the estimate of the probability that a person knows the formula of methyl alcohol. Now 400 independent experiments. Let's denote the outcomes as vector x. Let's write down the likelihood of our data observation, the probability of observing exactly this realization. Next, we will maximize the expression with respect to theta. Most often this is not done with likelihood likelihood, but with its logarithm function. Now we want to find such a value of theta that will maximize the likelihood. For this purpose, we will take the derivative with respect to theta, set it to 0, and solve the resulting equation. Okay. It turns out that our intuitive assessment is exactly the maximum likelihood estimate. Now let us apply the same reasoning to the linear regression problem and try to find out what lies beyond the mean squared error. To do this, we need to look at linear regression from our model naturally remains the same. But let us now assume that the random errors follow a centered normal distribution. Okay, let's rewrite the model from a new perspective. Since the example are taken independently, correlated errors is one of the conditions of the Gauss. Yeah, so yeah, well, I think I will finish on Han statistics today. Well, but yeah, not so easy for me, even if I like knew if I met it before, but it's still not easy to understand it properly. So let's try to do some break and then go to the statistics course again. Okay, so hard to keep these short breaks somehow. Okay, so I finished on okay, so what we have, so mom is grouchy and it's raining, so, and these two events are independent, so let's try to analyze it. So grouchy, not grouchy. So the probability of grouchy is equal to 1/10, and probability of rain is 1/3. So probability of grouchy and rain is equal to 1/10. So okay, so 1 day in the day 30 days she was it was rain and she was grouchy. Okay, so here we must have 2, the 9, and the 18. Okay. So okay, so let's watch on 2 tables, distribution on two tables.
Let's say that we are trying to understand a relationship in a classroom of 200 students between the amount of time studied and the percent correct. And so what we could do is we could set up some buckets of time studied and some buckets of percent correct, and then we could survey the students and or look at the data from the scores on the test, and then we can place students in these buckets. So what you see right over here, this is a two-way table, and you could also view this as a joint distribution along these two dimensions. So one way to read this is that 20 out of the 200 total students got between 60 and 79% on the test and studied between 21 and 40 minutes. So there's all sorts of interesting things that we could try to glean from this. But what we're going to focus on this video is 2 more types of distributions other than the joint distribution that we see in this data. One type is a marginal distribution. And a marginal distribution is just focusing on one of these dimensions. And one way to think about it is you can determine it by looking at the margin. So for example, if you wanted to figure out the marginal distribution of the percent correct, what you could do is look at the total of these rows. So these counts right over here give you the marginal distribution of the percent correct. 40 out of the 200 got between 80 and 100. 60 out of the 200 got between 60 and 79, so on and so forth. Now, marginal distribution could be represented as counts or as percentages. So if you represent it as percentages, you would divide each of these counts by the total, which is 200. So 40 over 200, that would be 20%. 60 out of 200, that'd be 30%. 70 out of 200, that would be 35%. 20 out of 200 is 10%, and 10 out of 200 is 5%. So this right over here, in terms of percentages, gives you the marginal distribution of the percent correct based on these buckets. So you could say 10% got between a 20 and a 39. Now you could also think about marginal distributions the other way. You could think about the marginal distribution for the time studied in the class. And so then you would look at these counts right over here. You'd say a total of 14 students studied between 0 and 20 minutes. You're not thinking about the percent correct anymore. A total of 30 studied between 21 and 40 minutes. And likewise, you could write these as percentages. This would be 7%. This would be, you might sometimes see when people are trying to interpret a joint distribution like this or get more information or more realizations from it, is to think about something known as a conditional distribution. Conditional distribution. And this is the distribution of one variable given something true about the other variable. So for example, an example of a conditional distribution would be the distribution of percent correct given that students study between, let's say, 41 and 60 minutes. Between 41 and 60 minutes. Well, to think about that, you would first look at your condition. Okay, let's look at the students who've studied between 41 and 60 minutes. And so that would be this column right over here. And then that column, the information in it, can give you your conditional distribution. Now, an important thing to realize is a marginal distribution can be represented as counts for the various buckets or percentages, while the standard practice for conditional distribution is to think in terms of percentages. So the conditional distribution of the percent correct, given that students study between 41 and 60 minutes, it would look something like this. Let me get a little bit more space. So if we set up the various categories, 80 to 100, 60 to 79, 40 to 59, continue it over here, 20 to 39, and 0 to 19. What we'd want to do is calculate the percentage that fall into each of these buckets, given that we're studying between 41 and 60 minutes. So this first one, 80 to 100, it would be 16 out of the 86 students. So we would write 16 out of 86, which is equal to 16 divided by 86 is equal to, I'll just round to one decimal place, it's roughly 18.6%. 18.6, approximately equal to 18. We would figure out 30 in order 30 out of 86, whatever percentage that is. And
okay, example. College grades. Small private college was curious about what levels of students were getting straight A grades. College officials collected data on the straight A status from the most recent semester for all of the undergraduate and graduate students. The data is shown. Distribution in dataset in highlighted below. What type of distribution is additional distribution? This measure of students level. What conclusion can we draw from the highlighted distribution? There are far more students with a grade than there are without. There are far more students with not. There are far more students without straight A than there are with. There are far more undergraduate students. There are far more. Officials at the college are curious if one level of student was more likely to get straight A's. That's the condition to say. Based on this condition, what can we say about the association between straight A's that are more likely to have straight A's than graduates? For instance, more likely to have straight A's than undergraduate. Straight A, we are more likely to be graduate students than undergraduate. This distribution shows that undergraduate students the choice is wrong because there are 300 total students with straight A and majority of them were undergraduates. This doesn't mean that undergraduate students are more likely. There were a lot of undergraduate students and graduate students, a lot of straight A graduates. However, a low percentage of undergraduate students got low. For this college, there is any association between the level of students and whether or not we are more okay. Do I need to watch Okay, maybe not. Okay. Ajay has been recording his outcomes for 3 games that he has played this summer. Here is his data. Chess, checkers, power. What is the best description of the distribution box? Imagine distribution of a game. This is imagine. This is conditions of games. Conditions of outcomes. Chess is interested in relationship between weather conditions and whether the downtown train runs. For a year, James records the weather each day as well as whether the train arrives on time or is delayed. Here are his results. Sunny, cloudy. Find the margin distribution of arrival status. Oh. No. Okay, so on time divided by total, so on time divided by total, maybe 0.9, 0.1. Non-geographical region and political affiliation then collect data about the political parties of US senators at the time and the regions of the US they represent. Results are in the table below. Oh well, I'm very tired again. Well, I think yes, tomorrow I will start early, so I will be in better shape than today's. Yeah, so okay, so can I? Well, yeah, well, I will finish for today. Yeah, not sure that yeah, it's really hard for me to keep it up. So yeah, well, yeah, I will start tomorrow early and maybe do some more work. I don't know. Okay, so thanks